All right, now let us do a short refresher on dynamics, mechanics and dynamics. We will just cover a few important aspects that I think we need to cover. And then after that, we'll be able to go straight into our main topic, that is motors. So today we're just going to look at some basic important things that we need, but not in depth. Right. So first, Newton's law. Newton law in 2D case. So when I say 2D, I mean on a plane. The classical dynamics classical mechanics is usually defined on 3D in 3D space, which makes perfect sense because that's the space where we live. Newton's mechanics can be absolutely abstract, but it also historically has been used to describe the real world. That's what we are using it for, to describe the real world. Real world is three-dimensional, but for some mechanisms, we could write a two-dimensional version of mechanics. And I think you probably have seen it quite a bit in high school and in your physics 1, and even theoretical mechanics. So second, Newton's law in 2D case look like this. The mass times acceleration in a certain direction is equal to projectional forces in this direction. In the x direction, same as in y direction, right? Oh, that is exactly the same as three-dimensional force case. Just the number of equations is 2 instead of 3. Okay, so far quite easy, quite easy. Newton's law, second law of Newton. Now, Euler's law, that is where things start to get interesting. Euler's law of motion in 2D case looks almost the same, okay? It says moment of inertia times second derivative of an angle, so orientation. So you can say angular acceleration, right? Is equal to sum of all torques acting on the body. That is Euler's law of motion in 2D case. So here we assume that the axis of rotation, around which we consider rotation, is perpendicular to the plane. So it looks at us, you can say. Then the positive direction of rotation would be, right-hand ruled. It would be, if you kind of wrap your hand around the axis, your thumb should stick along the axis. And you will notice this describes by the way, this describes counterclockwise, not clockwise, counterclockwise. Counterclockwise. All right. Now we can see similarity of these equations with Newton's law, right? It looks essentially exactly the same, right? Some inertia-like thing times second derivative equals to external force or torque. This is only true for a 2D case. In 3D case, Euler equation look like this, okay? Look like this. And if you're going to work with, let's say, drones or anything like that, where you have underwater robots, like anything where you have a rigid body moving through space, you have to use this equation. So you would see here that inertia times derivative of angular velocity is equal not only to torque, but torque plus this additional component, which is quite interesting. Quite interesting. There are tricks of changing frames in which you view all of this to make it simpler. But ultimately, all I want to say is, while you are going to use this equation, please don't forget that 3D motion is not described by this equation. It's only for 2D motion. Okay. Now let's get a few examples. So A pendulum can be described by the following dynamics equation. Here is the inertia of the pendulum. Here is the second derivative of the angle describing orientation of the pendulum. And here is the gravitational force. What do I mean gravitational force? Well, gravity, mg, that is the force, right? Okay. Now, this L times sine of phi is what makes it into a torque. So this force creates a torque. And the torque is L sine phi times the force, right? Let me give you a picture. So here's your pendulum, with the mass. L is obviously this length, right? This is L. You have mg going down here, right? This is mg. This is L. And how do you compute the torque produced by this thing? Well, for that, you have to compute this distance. This is the distance from the what is this distance? So let me explain a little bit more in detail. This is a line of action of the force, and here we have the place where the pendulum is connected, like the axis of rotation. So the distance we are talking about is the distance from the axis of rotation to the line of action of the force. And this distance happens to be L times sine of phi. Well, phi conventionally we Phi conventionally we define as this angle. The angle here is phi between the horizontal and the rod of the pendulum. That is the typical convention of how we define it. So, yeah, this is it. If we additionally have motor torque, then the equation becomes something like this. Previous equation plus torque. Okay. Quite simple. Quite simple. Now, as I said, a force applied to a rigid body at a point R generates a torque tau. The way it is described correctly in 3D case is something like this. It is a cross product of R and F. So the cross product of position of a point at which the force is applied times the force itself. And position, you could say with respect to the axis of rotation, if you want. But yeah, here we go into trying to be correct about 3D motion, which is I would try to avoid this kind of discussions here because we don't need it. It's much simpler in 2D case. In 3D case, we cannot treat it so lightheartedly. We have to be careful about what we are trying to do. Though it is there is no mystery there, but in 2D case much simpler. What we have is our torque is equal to R, which is the distance between the line of action of the force and the axis of rotation. So it is point-like in 2D space. So the distance between the line and the point is, let me draw it. Line, point. The distance between them is defined as having a perpendicular. Oops, sorry. You have a perpendicular line drawn through this point to the line. Okay, so you have this perpendicular line, and segment of this line, perpendicular line, that connects the original line to the point that segment, its length is called the distance from point to a line, right? So if you're saying distance from a point to a line, you could say, it is the segment of that connects this point to this line on a perpendicular drawn to it. Another way to say the same thing, and that is much more, I think, much more clean in terms of language, is that is the shortest distance, right? The distance between a point and a line is the shortest distance between the point and any point on the line. And that happens to be on the perpendicular. That is cleaner, but not as actionable. So, but yeah, both are fine. So this is the distance, and this distance is r. So this r here is this distance between the line of action of the force and the point of around which rotation is computed. And f here is just a magnitude of the force, just a magnitude of the force. So it's not a particular component of the force, it's magnitude of the total force. If we discuss separate components of the force, we need to remember that they have separate lines of action. So for example, force like this, here's a force. If we define it as having two components, let's say orange component looks vertical and violet component looks horizontal, okay? Two components, their sum is equal to the original force. We need to remember that the line of action for the orange component is this guy, right? So when we compute torque, we have to use this guy as a line of action. For the purple force, the line of action is this. So we have to use this one to compute torque. For the original force, line of action is this. So it will be, again, different line. And you can imagine if you have a point somewhere in space, let's say here, the distances will be different for each of those, right? Here's the orange distance. Here is the violet distance, okay? And here is the maroon distance, like original force distance. Different distances. So you have to be careful about those things when you compute. But when you get used to it, when you know that, okay, force, find its line of action, distance, use the formula 7, then everything becomes clean and simple. Okay. Nice. All right. Now, it is tempting to say that moment of inertia in 2D case is analog of the mass, that they are exactly the same, right? And it is tempting to say because look, moment of inertia defines how fast angular velocity changes when torque is applied. Mass defines how fast velocity changes when the force is applied. Right? So there is direct analog. It is only in 2D case. In 3D case, it is not the same. In 3D case, mass is still a scalar, while moment of inertia is a tensor. It is a symmetric matrix. Okay, 3 by 3. So need to be careful about that. Now, another way to think about moment of inertia is through kinetic energy. So kinetic energy in 3D case looks like this. You have mass times inner product of velocity, and that's for rigid body, okay? Plus angular velocity times itself, but with respect to this moment of inertia. Or another way, angular velocity in a product with inertia times angular velocity, right? Weighted in a product, something like this, right? Weighted dot product. So we have this kind of situation. In 2D case, it is simplified. It is simplified and it looks like this. We have a mass times Vx square, Vy square, and we have inertia times omega squared. So that's how it looks in 2D case. into decay. As you can see, much simpler, much simpler. So moment of inertia determines how much energy will the body acquire by the increase in the angular velocity. That I think is a good insight. Like, what is the moment of inertia? Essentially, it says energy will have to change this much when the angular velocity goes from 0 to, let's say, 1, or from 1 to 2, etc. Right? It is this scalar coefficient in the case in 2D case that determines how much the angular the kinetic energy has to increase. And increase of kinetic energy, of course, is related to work, right? Change of energy has to do with work. So that is quite useful thing to remember, because this is ultimately one of the ways you could recover this moment of inertia. If you know how much work is being produced to increase kinetic energy of the system, and you know the new angular velocity, you could recover quite easily the moment of inertia, right? While directly computing it can be challenging, but estimating it through kinetic energy can be simple for 2D case. For 3D case, not as simple. Okay, good. Now, moment of inertia of a point mass r meters away from the axis of rotation is given by this very simple formula. Okay, so this is like absolutely simple. mr squared. So for a point like mass, r meters away from the axis of rotation, this is what a moment of inertia is equivalent. This is the table formula. We have table formulas for a ton of things. I'm just giving you a few most useful ones. Okay, so this is a very useful one. It will be, by the way, exactly the same if we have a disk which is hollow inside and only has a rim. Okay, this is what we call a rim of a disk, right? This one. So if we compute, if it is a radius r, and we compute moment of inertia with respect to the center of mass, the axis at the center of the disk, the formula will be exactly the same. Exactly the same. Because essentially it is just a bunch of points whose individual moments of inertia governed by this formula, and the total mass is m. So after you take integral, you get this guy again. All right. For a solid disk, so a disk which has interior, right? Solid disk. Okay. Again, with respect to the center of the disk, moment of inertia will be computed like this. So there will be 1/2 coefficient. That has to do, as you can imagine, with the fact that some of the points are very close to the axis of rotation. So for them, the moment, even though their mass is the same as for the points on the rim, their moment of rotation is, their moment of inertia is much smaller. So we have 1/2 this coefficient. That basically you can recover by integrating. By integrating this formula 10 for each point in the interior of a disk. All right. Okay, though this is another famous formula. Now, for a centrally mounted rod, what is centrally mounted rod? Well, here is, 1 second, let me clear some space. Oopsies. Let me clear some space. Okay. Now, what is this centrally mounted rod? Here is the rod. Okay. And axis of rotation is at the center, like geometric center of the rod. Okay. So it rotates around the center. For this rod, the moment of inertia will look like 1/12 of mr squared. Notice mr squared is almost everywhere. The coefficient is the question. And again, you can recover it by integrating for each point on the rod. You can integrate do integral with equation 10, and then over dm, you can say, like a small point with a unit mass, and then you can find what you get. You will get this guy. For a rod mounted like pendulum, so if we mounted the rod this way, okay, it will be 1/3 of mr squared. So this is important thing to remember. Point like mass, so mathematical pendulum, would be mr squared. That is the moment of inertia. For a rod mounted like a pendulum, but a rod, not a pendulum, right? Not a mathematical pendulum, would be 3 times lower. Moment of inertia will be 3 times lower. If it is a centrally mounted rod, which is typical for motors, when you want to mount something, you don't want it non-symmetric because it will produce vibrations. So centrally mounted rod will be 1/12 the inertia. And a disc, you probably are not going to mount too many discs, but the motor output shaft is itself more or less a disc. It is a solid metal, so its like depth is irrelevant for us. What matters is its mass and its radius. It will be well described as a solid disk, and you have 1/2 times mr squared. Okay, so you can see all of those things, right? There are various tricks associated with it. Like for example, if you have a body which is almost the same as one of those, but is shifted, right? There is a special formula to compute that. Essentially, it looks very similar to this formula. Okay? It's addition. You add this shifted distance to the formula of inertia. Also, if you have a complicated form, like let's say you have a solid disk, but there is a hollow space inside, what we do is we compute inertia for the solid disk, then we compute the inertia for what would have been this hollow part, and then we subtract this hollow part from the disk overall. There are tricks, and all of those tricks are simple. Also, people often use software like SolidWorks or AutoCAD to automatically compute those things. AutoCAD automatically gives you a moment of inertia for each of your parts, but don't over rely on AutoCAD. If you cannot do simple 2D computations without AutoCAD, that is a problem. Okay, and the reason is because sometimes you want to test, and you cannot test if all your computations rely on AutoCAD. You have to be able to produce something manually and then check it with AutoCAD. For example, a rod, you can compute its moment of inertia manually, and then you can check with AutoCAD. Also, sometimes you want to do parameter identification, and that is, you can easily do it with like parameter identification techniques for 2D case. You shouldn't rely on AutoCAD in this sense. So I understand that this is a first impulse for every student who works with CAD is to use inertia parameters from the CAD, but don't abuse it. Okay, try to remember manual ways to do it and look into parameter identification. Without both of those, you will not produce good results. So that's just a wisdom that we acquire. Of course, you have to know how to use CAD, but don't over rely on it. Make sure you know other ways to estimate parameters. Okay. Now, let me see. We still have a little bit of time, right? I think just a little bit of time is still left. So let us think of mechanical energy. So mechanical energy is a sum of kinetic energy and potential energy. Okay, kinetic and potential. Together they produce mechanical energy. In 2D case, kinetic energy, as we said, looks like this, right? Vx squared plus Vy squared, times m 1/2. plus 1/2 g omega squared. Okay, so kinetic energy, quite simple. For a rigid body, of course, that's a single rigid body. Each rigid body would have the same kind of expression if you have a multi-body system, for example. Now, potential energy is a little bit more complex. It depends on what creates this potential, right? For example, gravitational potential energy, right? Gravitational potential energy usually looks like this. You have mg and then difference in height, okay? And difference in height you can compute as y minus y0. And y0 is the height at which you define your potential energy as 0. The reason is, you know, you can always go down, right, in potential field, unless you consider potential field in 3D case, but also not uniform, but like this true potential field generated by a massive body. So it is kind of like a radiant, like radiates in every direction. And then you have true zero when you are like at the very center of this potential field. But for uniform potential field, which is what we usually do when we say, for example, mg, like gravitational force is mg. For this type of potential field, we have to work with differences. And there is no true zero, right, for this potential field. So we have to define a zero. And this is important. This is important. Sometimes we say, oh, when the body is on the ground, this is zero potential energy. When it goes up, it is non-zero. That works well for things that are thrown up and so on. But it is not always how you have to define potential energy. So, just be aware. mg times difference in height. Okay. Now, linear spring is very similar. Linear spring potential energy. There you have 1/2, notice, right? Similar to kinetic energy now. Stiffness coefficient, K. Stiffness coefficient, K. And then the difference between the current state of the spring and non-deformed state of the spring, right? So let's say current length of the spring is 10 centimeters, but in non-deformed state, it will be 14 centimeters. So 4 centimeters difference is what we have here. And you are going to square it. You're going to square it. Okay, quite interesting, quite interesting. That will be expression for linear spring potential energy. All right. With potential energy, one of the tricks you can do is you can remember that potential of force generated that associated with potential energy usually can be computed as a partial derivative of the potential energy with respect to the coordinate. So if we here take partial derivative of p, what we get is this guy will go away, right? Partial derivative with respect to y is going to be 1, with respect to y0 is going to be 0. So we get mg, correct, right? That is correct for the expression for gravitational force. If we take a partial derivative with respect to p here, pi here, right? What we get is this square is going to go away. This 1/2 is going to go away. And what we have is k minus k times difference in length, right? K times deformation. That's exactly the expression for the spring force, linear spring force. By the way, angular spring has exactly the same expression. So you can use this expression for angular springs too. All right. So that is potential energy. So you need to remember the source of potential energy to compute it. Okay. Elastic deformation, gravitational forces are most typical source potential energy. Now, the change of total energy of the system is equal to mechanical work produced by active forces. So delta T plus delta P, so change of total mechanical energy, right? The total energy is equal to sum of all work, mechanical work produced by active forces. Okay. Good. Right, active force like Fi, or torques, by the way, tau I. How do we compute work produced by a force? Well, in 3D case, it would be something like this. Work is equal to integral from initial point to final point, right? So integral over time. And integral over what? Over what we call power. So inner product of velocity times force. That might not be what you saw in high school, but hopefully you saw it in Physics 1 or theoretical mechanics. So work is integral over power. Or in other words, it is integral over inner product of velocity and force. Okay. As you can see, since we integrate, like if force is constant, if force doesn't change, it looks like force can be taken out of the equation, and it looks like inside the equation will be integral over velocity, which is like a path, right? And then we get this familiar high school expression where work is a path times like how much how much movement was made times the force. So that is a comforting thought that the expression 13 can be made back into our delta S or whatever, like delta pass times force. Okay. Okay. Now, in 2D case, all of this is a little bit simpler. So let's assume that F and V are collinear. So they point into the same direction, okay? In this case, we have, this expression where if we can even define velocity as derivative of a position, right? We have this expression. And if F is constant, then what we see is A is equal to position at the end minus position at the beginning times F. Great, that is absolutely great. That's what we like. So for a torque, it will be kind of the same. If torque is constant, then work is given orientation at the end, orientation at the beginning, minus orientation at the beginning. That's it. That's how we can get these expressions. Okay. So this is how we can get expressions for the work. Finally, I think that's the last slide. Yeah, that's the last slide. Finally, power. Notice I already told you that this is power, right? Mechanical power. We can define it various ways. Like we can define it as velocity times force. By the way, notice in 2D cases is also true, because both velocity and force in 2D cases are still vectors. So you still have to find inner product of those two things. For torque and angular velocity, it is simpler because both of them are scalars. In 2D case, angular velocity is a scalar, torque is a scalar. So they just have a normal product. Right? And also, power is a derivative of work, just as work is integral of power. Okay. So power is instantaneous quality. It exists at each point of time. It has a different value each point of time. Work does not exist at a point of time. Work is a result of time passing. Work exists only as a difference between what was then and what is now. So it's very important to realize that work is not something that you can compute for each point of time. Instead, you compute it on the interval of time. While power exists at each point of time. So important relations. But power is also always scalar, same as work, because power is essentially a derivative of work. So just things to keep in mind. Just things to keep in mind. Okay. Now, of course, we could find quite interesting relation between mechanical energy and power, sum of all powers acting on the system would be equal to derivative of kinetic plus potential energy. Right? Sounds quite reasonable, right? Like how fast does the full energy of the system change? Well, it depends on power of the forces acting. That makes sense. That makes sense. All right. That was it for the refresher. Do we have questions? If not, then let us be, notified that this is the end of refreshers, and also we, not only mechanical in terms of mechanical electrical systems, but also in terms of like Laplace, even some basic analysis tools from control theory. Next lecture, we go straight into motors, and we are going to spend 2 lectures non-stop on the motors. So be prepared. It is absolutely critical. It's like critical material from the course. And that is like one of the main outcomes of the course is for you to understand DC motors. So next lecture, please make sure you have time to attend and so on and so forth. All right. Thank you for finding time today, and we'll see each other next week. Goodbye.
Goodbye.
Goodbye.